Let us solve some numerical problems based on applications already discussed in part 1. And these applications are such that the differential equations in them are in variable separable form. The applications are temperature of a cooling body, radioactive decay, population growth, etc. And the numericals we are going to discuss in this presentation. These are the 3 problems. We start with one by one. So our first problem is regarding population growth. For a town, the initial population is given that it is 40,000, and after 40 years the population becomes 60,000. And the fact is also mentioned that it increases at a rate proportional to the population at that time. And we have to calculate the population in another 20 years, that means when t is equal to 60. The differential equation regarding this population growth and its solution is already discussed in the previous video. So if you have any doubt, refer that video. Here all the steps are given, but I am not going to explain them in detail. So this is the differential equation and its solution last is t is equal to c raised to kt. Now we want to calculate these two values first, c and k, using the given information. And the information is p at t equal to 0, that is p of 0 is 40,000 and p at t equal to 40 is 60,000. So if we put first value, that means put t equal to 0 in this equation 1 and p equal to 40,000, since e raised to 0 is equal to 1, we get c is equal to 40,000. Putting that value of c in equation 1, we get p is now equal to 40,000 e raised to kt. Now we want to calculate value of k. For that we are going to use this second information. So when t is equal to 40, t is equal to 60,000. Putting these values in this equation, we get 60,000 is equal to 40,000 into e raised to 40k. And therefore, e raised to 40k is equal to 60,000 divided by 40,000, which is 3 by 2. Now from here, either we can calculate the value of k explicitly and write the equation first, and then putting t equal to 60 we can calculate the value of t. That is one standard method. But the equation is not asked us. That means write the population as time t, or determine the function or determine the population at any time t. That is not asked. Just asked in the problem is the population in another 20 years. So you can use this shortcut method instead of writing this equation in this form and finding the value of k explicitly. Here you can find that the value of e raised to k is 3 by 2 raised to 1 by 40. And I am going to put value of e raised to k in this equation. And so my p is equal to 40,000 into 3 by 2 raised to t by 40. And then by putting value of t equal to 60, I will get this, and using calculator the approximate value is 73,485. Let me explain the another method also in detail. We have e raised to 40k is equal to 3 by 2, which is 1.5. Therefore k is equal to 1 upon 40 into ln of 1.5, which is this 0.01014. Now by putting this value in the equation, we get t is equal to 40,000 e raised to 0.01014 t. And then putting value of t is equal to 60, we will get the same answer. Sometimes you can do this also. So this is our first problem. In the second problem, a hot water is kept in a room of temperature 25 degrees Celsius. And at initial stage, that means when t equal to 0, temperature of water is 100 degrees Celsius, and within 10 minutes it reduces to 80 degrees Celsius. This is given to us. We want to find temperature of water when t is equal to 20, and we want to find t when temperature is 40 degrees Celsius. This is the problem based on Newton's law of cooling. The differential equation and its solutions, they are given here for the sake of completeness. So the solution is theta is equal to theta naught plus C raised to minus KT. And now we will put all the values given in the problem. Here theta naught is equal to temperature of surrounding, that is room temperature, so it is 25 degrees. At T equal to 0, temperature of water is 100 degrees Celsius. So theta of 0 is equal to 100 and theta of 10, that is after 10 minutes, T equal to 10, theta is 80 degrees Celsius. So these values are given to us. Now putting these values, since T is 0, e raised to 0 is 1 and theta naught is 25, we get 100 is equal to 25 plus C. So C is equal to 75. Putting values of theta naught and C, we get the equation is theta is equal to 25 plus 75 e raised to minus KT. Now to find the value of K, we are going to use this information. So when T is equal to 10, put theta is equal to 80. Therefore 80 is equal to 25 plus 75 into e raised to minus 10K. Therefore, e raised to minus 10K is equal to 80 minus 25, which is 55 divided by 75. And therefore, 10K is equal to ln of reciprocal of this, which is 75 divided by 55. And therefore, K is equal to ln of 75 minus ln of 55 divided by 10, which is 0.031. So, now after putting value of theta naught, C and K, our final equation is theta is equal to 25 plus 75 e raised to minus 0.031 T. Now when T is equal to 20, putting that value here, we can calculate value of theta using calculator, and that is 65.35 degrees Celsius, 34 degrees Celsius. The second question is, we want to calculate value of T when theta is 40. So put theta is equal to 40 in the equation. We get 40 is equal to 25 plus 75 e raised to minus 0.031 T. And therefore, e raised to minus 0.031 T is equal to 40 minus 25 divided by 75, which is 15 upon 75, which is 1 by 5. And so, 0.031 T is equal to ln of reciprocal of this, which is ln of 5. And so, T is equal to ln of 5 divided by 0.031, which is 51.92 minutes. And that is our second problem. So let us start third problem. In the third problem, we have to calculate age of a fossil OLC. What is given to us? That in that fossil at present, the ratio of carbon to carbon 12C6 in this mummy is 52% of that of a living organism. That means the ratio in atmosphere. Or in living organism, they are same. You can check these facts with our previous video also. Video on applications part 1. Now, if we start with let MT be the amount of radioactive carbon at any time t and writing the differential equation and writing its solution, we get M is equal to C raised to minus KT. Now we want to put the values. Since it is radioactive carbon, we know its half-life period, it is 5750. That means when T equal to 0, if initially it is M0, at 5715 it is M0 by 2. So using this information, we can find the values of C and K. See, if we put T equal to 0 here and M equal to M0, we get C is equal to M0. And therefore M is equal to M0 e raised to minus KT. Put T equal to 5715 and M is equal to M0 by 2. We can find the value of K. This M0 will get cancelled with this M0 and therefore e raised to minus 5715k is equal to half, and therefore 5715k is equal to ln of 2, reciprocal of this, or k is equal to 0.00012. Putting this value in the equation, we get m is equal to m naught e raised to minus 0.0012 into t. Now we want to find the value of t, where m is 52% of the original ratio. So m is equal to 52 m naught by 100, and so putting that value, we get 52 m naught by 100 is equal to m naught into e raised to minus 0.00012 into t. This m naught will get cancelled again, and so e raised to minus 0.001t is equal to 52 by 100, which is 0.52. Therefore, t is equal to 1 upon minus 0.00012 into ln of 0.52. This number is also negative, and so you can get the answer is 5450 years. That is age of that mummy. Now you can guess it also, because half-life period of 14C6 is 5750 and it remains 52%, that means just more than half-life, and therefore it is 5400, just less than half-life period, which is 5450 years. Okay, in the exercise, 6 questions are given to you. All these questions are based on these applications only. Try them. If you have any doubt, contact me on my mail ID jignasacademy@gmail.com. If you like the video, share it with your friends, subscribe the channel. Don't forget to press the bell icon so that you can get the notifications of more such videos. Thank you.